Hello, this video is for Stat 110, Module 1, Part 3. It includes the staring example. Okay, let's go ahead and get started with this example. So the staring example is from a study that was done by Rupert Sheldrake. He has done a variety of studies regarding the consciousness in animals and in people. I think the easiest way to describe this experiment is just to watch the YouTube video that Sheldrake has put together for this experiment. That link is there highlighted on the screen for you. I will play the video here just for completeness, but it will have a little bit of echoing. You're going to want to pay attention to about the 1 minute and 54-second mark is a statement that is made by Dr. Sheldrake. Okay, let's go ahead and play this video then. You can hit pause if you'd like and just click on the link here. It will not have the echoing effect.
Fields are regions of influence. It's easier to see what fields are with magnetic fields. These balls are little magnets, and as I drop them onto the plate, the balls attract each other or repel each other. They turn around, and so they all join up in patterns. There's a self-organizing property in fields. They're inherently integrative. And what I'm suggesting is that there's another kind of field called morphic fields, which organize the bodies of animals and plants and organize the activities of brains and minds.
Rupert believes that morphic fields are what allow birds to fly in perfect formation, what guide the mass migrations of herd animals. And he also believes they are the reason we get that uncanny feeling when someone stares at us. He has even run a series of experiments to try to prove that this sense is real.
Not looking.
You either look or you don't look in a random sequence of trials at somebody else, and they have to guess in each trial if they're being stared at or not.
Not looking.
The starer should concentrate their mind on the person they're looking at. When I do it, I also think of the person's name.
Looking.
So I can concentrate all my attention on them. When I'm not looking at them, I look at the floor or I close my eyes, and I think of something completely different.
Not looking.
Brilliant. 14 right and 6 wrong. Something's going on. And although the effect's not big, it's consistent and it's repeated over large numbers of trials.
Rupert has gathered a body of evidence that shows people really do appear to know when they're being stared at. For him, it supports the idea that our bodies are surrounded by morphic fields, an invisible extension of ourselves.
What I'm suggesting is that our minds work through extended fields that stretch out far beyond our heads into the world around us, linking us to other people and to our environment.
Okay, so that's the video for the staring example. We are now going to consider that statement that was made, and in particular the brilliant 14 correct, 6 wrong statement. We're going to use a statistical model and simulate outcomes from this type of experiment. So in order to use a statistical model in this situation, or simulation model, we need to know the number of outcomes, and this individual had a total of 20 outcomes, 14 correct, 6 wrong, so there's a total of 20. And then we also need to specify a probability of success, which is just the likelihood of obtaining a correct response. Now, similar to the deafness example, we're going to have to decide which situation are we going to simulate. In the deafness example, we simulated the situation of somebody being deaf in order for us to try to figure out whether or not that individual was lying. Here what we are going to do is we are going to simulate an individual that does not have the ability to identify when someone is staring at them. So we do the situation of not having the ability. And we're going to use the information from this particular woman, which had 14 correct, 6 wrong, and evaluate that against a person that does not have the ability. Okay, so for this example, as I said, we have a total number of trials is 20, and the likelihood or chance of a correct response is 1 out of 2. Again, this individual was given 2 choices, either to look or not look, were the 2 choices that were given. She had to make a guess, or a person without the ability is going to have to make a guess at whether or not the individual was looking or not looking. Now we convert that look or no look into a correct or incorrect response. Okay, so the 2 outcomes that I care about is whether or not the response was correct or incorrect. So let's talk a little bit about the expected value. The expected value is just going to be equal to the number of trials multiplied by the probability of a success, or probability of correctly identifying that she's being stared at. And again, we are doing this under a situation for an individual that does not have the ability. So that probability we know is going to be 1/2. In fact, that's why we simulate this situation, is we know that for a woman that does not have the ability, then she's going to have a 1/2 chance of being correct and a 1/2 chance of being incorrect. So we can simulate an individual that does not have an ability. We can do that without any biases. And we know that that probability of correct is indeed the correct probability to be using in that situation. So 20 times 1/2, the expected value there is 10. So once again, we're going to have our pyramid centered at 10, and then we're going to have that inherent variation that exists above and below that value. So here, we're going to have that pyramid shape, or that reference distribution is what that's called, and the shaded region is going to be the situation of no ability. Now, if this woman has the ability, then she's going to be scoring more correct than what we would expect from an individual with no ability. So if a value is on the upper end of this distribution, that is going to indicate that they have the ability to identify when somebody's staring at them. Now, one of the main aspects from a reference distribution that we get is the amount of inherent variability. So here I have another picture where I have a lot of inherent variability. So this reference distribution or pyramid stretches all the way down to 3 and all the way up to 17. Or am I in a situation where my reference distribution doesn't have much inherent variability at all? So here my reference distribution, or my pyramid, goes down to about 8 and up to about 12. Now we need to decide, or we need to look at our reference distribution to make a decision about whether or not she has an ability. The reason we use the reference distribution is so I can kind of find the edge of where the no ability range is at. In this particular picture, it's at 14. In this particular picture, the edge is up here at 17. So a response of 14 here is not going to indicate that she has the ability, because it's within the realm of the no ability situation. Or am I in a situation like I am here on the third graph, where 14 is indeed kind of an outlier, or is an unusual outcome, or an unlikely outcome? Here the no ability range again goes from about 8 to 12. So if I'm in this situation, an individual that scores 14 out of 20 would actually have the ability. So we need to use a reference distribution. We need to construct and understand what that reference distribution looks like in order to separate these 3 different situations. All right, So the big question here that the statistician has to wrangle with and understand is, or to answer, I guess, is does 14 out of 20 provide enough statistical evidence to suggest that the woman in the video does indeed have the ability to identify when somebody's staring at her? And what we need to do, or our approach, is to determine whether or not 14 is an outlier against the situation in which a woman does not have the ability to identify when someone's staring at her. Okay? All right, so let's set up a simulation model here. And we are going to use an app that was written by Todd Iverson, who is a faculty member here at Winona State University. So you can go ahead and click on that app. I'm going to actually highlight it and put it into a new tab, just so I can go back and forth between the notes. So how do we set up this simulation model? Well, I need to know what the two outcomes are, which I've previously said that they are going to be correct and incorrect. Now again, the individual in that woman in the video identified either look or no look, but we convert those guesses or outcomes into either a correct or incorrect. Again, I need to evaluate the 14 out of 20 correct. The probability here is going to be 50%. Again, this is the probability for a correct outcome. The n here just represents the number of trials, or the sample size, and that's going to be set to 20. And then I'm going to want to select the count from my statistic. To actually run a single set of trials, I'm going to need to click the spin button here. Okay, so let's go over to the app and show you how this app operates. So again, the two outcomes here are going to be correct and incorrect. I'm going to need to specify the probability of a correct response. So this, in the app, this P here is just the probability for the success outcome. And we just generically label this a success or a failure. There just needs to be two outcomes. And then the n value here is going to be 20 because a total of 20 trials were completed by that woman. We're going to need to select the statistic is going to be the count, because I am interested in the number of correct outcomes. Now once this is done, the rest of the app will present itself and I can start to gather outcomes. So let's go ahead and click the spin 20 times button here in the left-hand side of the screen. What the app is doing is just simply mimicking the 20 guesses that would need to be made for a person that does not have the ability. So that spinner there ran a total of 20 trials. Down here on my graph, I can see that out of those 20, I got 6 correct and 14 incorrect. I can click spin again and I'm going to get another set of 20 outcomes here. This time I got 8 correct and 12 incorrect. What we should be getting, or what the expected number of correct, is going to be 10. So that's going to be the most likely outcome. So here we got 12 this time. If you want to turn off the animation, just select the box and the spinner will operate more quickly here. So that time I got 11 correct. There's 9 correct. 9 again, 8, 9. So you can just see this value changing here. I can do that many, many, many times. Okay, and again, this is mimicking a situation in which the individual does not have the ability. And I know that because I've set this up here at 50%. Okay, so that count success there is the value that we are interested in. And we're going to try to understand how does that value change if I do this experiment over and over and over again. So here I've gathered 10 different responses. First time I got an 11, the second time I got a 9, third time a 13, all the way down, the last time I got a 10. And those responses are just listed here in the table. I went ahead and put those on the number line here. This is going to be a number line for the number correct. The number line is going to go from 0 all the way up to 20. And we can see that the dots are going to start building up around the value of 10 here. What we are trying to do with this graph or with this simulation is again trying to figure out how likely or unlikely is it that I would see a value of 14. Okay, so we have a set of questions here that I'd like you to answer. So go ahead and hit pause and try to answer the first set here. Okay, so how many simulated outcomes are represented in this plot? Well, there's going to be 10 of those. I have 10 dots on that plot. So let's consider one of the dots here. Let's consider one of the dots at 11 here. If I ask for a description of the process for how that value was obtained, you're going to need to identify 3 things. The first is that you had 11 correct. So if I'm asking you to describe the dot here at 11, that indicates that I had 11 correct. You need to tell me out of how many. So I don't know if 11 correct is a lot unless I know how many repeated trials were done. So the second element that you need to communicate when you're talking about what a value means or what it implies is to identify out of how many. So the first part of that statement is going to be I found this individual or this set of repeated outcomes. Well, I got 11 correct out of 20. Now the last component is a little bit about how did you obtain this pyramid. So it says describe the process. Well, part of that, an important part of that, is that you did this under a 50-50 scenario, so that I would know or be able to identify that the expected value here is at 10. What we're going to do eventually is just start moving this pyramid around. So this pyramid might slide up a little bit, or it might slide down a little bit. So I need to know where that pyramid is centered at in order to figure out whether or not 11 is a likely or unlikely outcome. Okay, so quick recap there for question 2. It actually requires 3 components. How many correct, out of how many, which would be 20, and that you are mimicking a situation where a woman does not have the ability. Or you could say that I constructed this simulation under a situation of 50% correct. Likely outcomes for number 3 are going to be values around 10. Unlikely outcomes are going to be values far away from 10. All right, so let's look at an example where I got more than 10 repeated outcomes. Okay, so here I only did 10. Down below, it looks like I did 100 repeated outcomes. And that's going to give me a better idea of where the edge of this reference distribution sits. It would be even better to get like maybe 200 repeated outcomes, or to do a total of 200 repeated simulations. So it's important that you do enough repeated simulations so that you know where the edge of this reference distribution kind of settles down at. Again, our goal here is to determine whether or not 14 is an likely outcome or an unlikely outcome. And if it's unlikely on this end of the distribution, then I'm going to believe that she does indeed have the ability. All right, I'll go ahead and hit pause here and let you answer the rest of those questions. Okay, let's just do question 7 quickly here. Consider the white dot, which is right there. Describe the process by which that dot was obtained. So a complete response there would be that we got 8 correct out of a total of 20. And that value was obtained under a 50-50 situation. Consider the value of 14. In your opinion, does 14 provide enough evidence? To be honest, that's right on the edge here. So 14 is right kind of on the edge of that distribution. We did obtain 3 times. So I got 3 dots here at 14 and actually one up here at 16. So 3 times I obtained a value of 14 under a situation of no ability. Okay, so these dots again were under a situation of no ability, and this outcome from the woman in that video agrees with 3 of those. Now granted, 3 out of 100 is not a lot, but it is within the realm of the no ability dots here. Statistician would have more confidence in using a graph on 100 repeated outcomes instead of 10 when determining kind of where that edge of that distribution is, or that cutoff value. So we'll talk more about that in the next handout. Where is the cutoff value between the likely outcomes and the unlikely outcomes? Okay, that does it then for this video. Thank you.